Hey guys, this is Rakesh Arai, your chemistry mentor, and welcome back to Teach Tigers. Today is the lecture 2 in a series of lectures dedicated to thermodynamics. And I hope you went through the first lecture. We had some fun and we talked about many things. So I highly recommend you go through lecture 1 before you start with lecture 2. And let's start with lecture 2 today. What do we have? First, we are going to talk about recap of lecture 1. In lecture 1, we defined state and we said state is what defines all macroscopic properties of our system. And we highlighted the term macro. Macro is different from micro. And the way it is different is micro is very small, atoms, things you can't see, molecules, electrons. But macro is large, tangible things you can touch, things you can feel, things you can see. So in a thermodynamic state, so you'll see the term state at many different places in quantum mechanics, in thermodynamics, and in different fields of physics, but here we're talking about a thermodynamic state. A thermodynamic state defines all macroscopic properties. And we also said that these macroscopic properties, such as pressure, volume, temperature, they're also important as state variables. But before that, state variables define the state of the system. We talked about that. We can define the state of the system using pressure, volume, temperature, number of particles. So this seems like a cyclic definition that state variables define the state defines the state variables or the macroscopic properties. So how do we go about it? This seems all very confusing, except that there's a very clear way to look at it. What we usually know are the macroscopic properties. Some of them, we know some of the macroscopic properties because they're easy to measure. For example, pressure is easy to measure. We can simply take a pressure gauge. Easily available, commercially available. Even you can go and buy a pressure gauge. We can measure volume very easily using Arrhenius principle. We can measure temperature very easily using thermometers. But we can't measure everything. You can't measure heat capacity at home, for example. You can't measure other properties like elongation constant very accurately at home. So what we do is we go from point 2 to point 1. There are a few state variables which are easy to calculate. They help us in determining the state, and then state helps us in determining the remaining properties that are difficult to calculate. So we always start with measurement. That's one key concept in thermodynamics. Thermodynamics is although it looks like a lot of theory, but at the core of it, it's an experimental field. All right, moving on. The state variables, pressure, volume, temperature, number of particles, they're all state variables. They help us in defining the state. What is a state? It's determined by P, V, T, and N of our system. Another thing that we talked about is that units are important. If I can take one simple example, suppose that tomorrow you go get a job and they tell you, the HR tells you that we are going to pay you 60. Are you going to take the job? The question there is 60 what? 60, 100, 60,000, 60 paisa? You won't do a job for 60 paisa, right? $60. So units are important. We should know what we are talking about. We should know that. In any question in thermodynamics, you should always take a look at what units are given to you. In exams, you will have some very straightforward questions with a formula that's already there in your brain, and fatakse you'll solve it. Fatakse, but you will miss the units. And I can assure you there will be an option for calculating the answer with wrong units because the examiner wants you to get it wrong. So you have to be careful. And in your mind, you would have gotten the right answer. Option B, correct. Numerically it matches, but units don't match. Moving on, we talked about STP, standard temperature and pressure, and we talked about SATP, standard ambient temperature and pressure, which is also known as normal temperature and pressure sometimes. Ambient is the key term here, or even normal, because they mean room temperature. almost room temperature, which is 25 degrees Celsius. So whenever you see the term ambient, normal, they mean room temperature. On the other hand, STP corresponds to 0 degrees Celsius. Both of them have about pressure 1 atm. Here 1 atm. This is 1 bar. So when it comes to calculations, it doesn't matter because 1 atm is approximately 1 bar. There's only a 1% difference in them. But I hope it doesn't happen. If the examiner asks you exactly what STP is it 1 atm or is it 1 bar? Then you should tell STP is 1 atm, NTP, SATP are 1 bar. Then we talked about a very important formula, the conversion of Kelvin degree Celsius, Kelvin to degrees Celsius temperature conversion. And the value that I asked you to remember, you should like just keep it in your mind because it's going to show up again and again and again. And the value is 273.15. 273.15. How does it help us convert degrees Celsius into Kelvin? We just take, so if we are given a temperature X in degrees Celsius, X can be 100 degrees Celsius, 20 degrees Celsius. To convert it to Kelvin, we just add this number 273.15 to X. One example that we took was, what is the boiling point of water in Kelvin scale? We know the boiling point of water is about 100 degrees Celsius. On Kelvin scale, it will be 100 plus 273.15, which is 373.15. Similarly, I could ask you, what is the freezing point of water? Freezing point of water on degrees Celsius scale is 0. And to convert it to Kelvin, we add 273.15. So 0 plus 273.15, that gives us 273.15. So 273.15 Kelvin is the freezing point of water. 373.15 Kelvin, boiling point of water. What are we going to do today? Today we're going to talk about system and surroundings. You might have heard me say this word plenty of times in the last lecture. System. What is our system? A water bottle is our system. You are my system. But I never clearly defined what a system is. And it is important to do that. It is important to define what we say so that you don't have a confusion. I don't have a confusion. Some person sitting in Finland doesn't have a confusion. Everyone should know what I mean when I say a term. So we're going to define system. We are going to define surroundings. And then we are going to talk about different types of system that we see in our daily lives. Actually, in our daily lives. Then we're going to talk about types of system boundaries. And before that, we should also know what a system boundary is. And we are also going to talk about equations of state. In the last lecture, I mentioned how variables of state, they're somehow interrelated to each other. Like you change temperature, pressure also changes. You increase the volume of a chamber of gas, the pressure reduces. You heat up a chamber of gas, the pressure increases or the volume increases. So somehow variables of state, they are interrelated. They are connected to each other. And this connection between them is determined by the equation of state. So we're going to talk more about what equation of state is. And all right, we'll come to that. There's a very nice surprise given in the heading itself. Maybe you can figure it out, but we'll come to that. And next we're going to talk about internal energy of the system. Very, very important topic. You need to know what internal energy is to start doing thermodynamics. There's a lot more coming after internal energy. But first we should understand what internal energy is. To start with, let's define what a system is. System is the part of the universe we are trying to study. So what are we trying to study? Study as in, does it mean studying like you're doing, studying for your exams? So part of the universe you're trying to study maybe JEE exam, maybe NEET exam. No. So by study here, we mean study that scientists do, that experiment, the things we are measuring properties of, right? So if I take a water bottle and I start asking questions, the first question I could ask is, what is the volume of water present inside it? You always get Bisleri bottle. There's a small bottle, 500 ml. Then there's a 1 liter bottle. There are even smaller bottles, 250, 200 ml. The bigger bottles, 5 liters, 2 liters, 20 liters, right? So that's the first question I can ask. So now I'm studying the water bottle. Similarly, we study any system. I could next ask what minerals are present. Is there sodium present inside it? Is there some amount of chloride present inside it? There are certain ions that are not good for usage. For example, calcium ions, magnesium ions, they cause water to become hard. Right? You must have heard about hard water, soft water. Usually, like in certain states, you find hard water. In other states, you find soft water. Hard water has calcium ions, magnesium ions, and it doesn't. It does okay. And you can actually do an experiment to find out if the water is hard or soft. All you have to do is you have to take a bit of detergent, mix it in tap water, and see that after a while, does it form a whitish precipitate? If it does, then the water available in your place is hard water. Hard water. These days, detergents they account for water being hard, so that the cleaning is proper. Cleaning of clothes or utensils, it's proper. All right. So it's part of the universe that we are trying to study. It can be anything. It can be anything. I can start studying a water bottle. I can start studying this pen. I can start studying this board. I can start studying the air present inside this room. I can start studying anything. And that becomes my system. And system can be open, it can be closed, or it can be isolated. So these are the different types of system that we see. And what are these systems? Most often we come across open systems. Open systems are systems that can, so if I draw my system, an open system would be something that can exchange, the first thing it can exchange is mass. And the second thing it can exchange is energy. So it can exchange mass, it can exchange energy. Very good example would be a hot cup of coffee. From a hot cup of coffee, you see water vapors come out. Water vapors are massive particles. By massive, I don't mean heavy. Massive as in they have mass. So you see water vapors come out, and you also see that the cup of coffee cools down after a while. It is giving off heat energy. It is giving off heat energy. So it can exchange both mass and energy. The next type of system we have is a closed type of system. A closed system, if I draw, can exchange energy, but cannot exchange mass. And the way we're going to show it is that the mass has not been exchanged. Right? So here mass can cross across, it can go outside, come inside. Here mass can't go outside, come inside. But energy can. And what would be an example of that? An example of that would be a closed water bottle, right? You buy a newly packed, sealed water bottle, so no mass has entered inside it. That's why we can trust the water inside a packaged water bottle to be free of any bacteria, free of any other dust particles, because it's sealed. No mass enters inside the bottle once it is sealed. But you can keep it in fridge and it becomes cold. If you keep it outside, it becomes warm. And you can keep it in sun to make it hot. So it's exchanging energy across the boundary, but not mass. So example of a closed system would be a closed, sealed water bottle. And next we have isolated systems. Isolated systems are the complete extreme. They're neither mass can cross the boundary and neither energy. So mass, energy, everything just stays inside. Very difficult to give an example of a isolated system. Very difficult. But thermoses, modern thermoses, not the old ones. You'll sometimes find, if you have ever seen a thermos probably 10 to 20 years back, and if it's too old and you don't need it, you can actually break it and see what's inside. You know that thermoses are really fat, but they store a very small amount of substance. anything. Like you can pour maybe like 2 glasses of water in a thermos that seems like it can hold like maybe 10 glasses of water. And if you break the outer layer, what you will find inside is insulation. You'll find inside insulation. So if I quickly draw it of like a thermos, really fat, but inside it's like just a small quantity that can actually hold something, and all this is insulation. Insulation, some type of foam is present over here that doesn't allow energy to cross very freely. But the old thermoses, they're not very efficient. One of the reasons they're not efficient is they're so heavy, they're so bulky, and you have to put like so much insulation to disallow energy to cross. But modern thermoses, and you can actually look at the cover, the box of any thermos that you buy should have vacuum insulated or vacuum technology. And the reason for saying that vacuum is instead of having foam over here, there is instead vacuum. And there is no better insulator than vacuum. There's no better insulator than vacuum. No matter how efficient your insulator is, it can at least cross a little amount of heat, right? A little bit of vibrations can happen. So even if your insulation is very good, and there are a few, so this is my insulation. So even then, like a little bit of vibration will cross. But if there are no atoms, present, then it won't cross. The heat can't cross like that. Another thing that's present inside modern thermoses is a silver lining on the inner surface that does not allow radiation to escape. So very well insulated, the modern thermoses. So that's an example of isolated systems. All right. So 3 types of system: open, coffee mug; closed, sealed water bottles; and isolated, modern thermoses. Let's move forward. What are surroundings? So we defined our system. Now we have to define our surroundings. And surroundings are part of the universe affected by the system. So we have a system. System does something. And then it affects the surroundings around it. For example, if you switch on AC inside a room, the outside gets hotter, right? If you switch on AC inside, your room gets cold, but the outsides get hotter. What else? What else can we say? All right, like another example, let's take the coffee mug again. Like coffee mug is proving to be a very useful example for us. When coffee mug cools down, the surroundings become hot, right? Like if you don't believe me, like place your hand on the coffee mug and you will feel your hand becoming warmer with time. So when coffee mug cools down, the surroundings become hot, right? The atmosphere around it becomes hot. But there's a tricky word over here which is affected by the system. And what is affected and what is not is a difficult question to answer. So we obviously don't say that coffee mug affects how the sun operates at that distance, right? We just take like a small, maybe our laboratory at best, and that's the surroundings, part of the universe affected by the system. Next, there's a question for you, a quick question. What are the surroundings for an isolated system? You already know the definition of surroundings. Based on this definition, what can you say about the surroundings for an isolated system? The answer is they are non-existent. Because isolated system does not affect anything outside. It doesn't let mass escape. It doesn't let energy escape. So it does not affect anything. And as a result, it has no surroundings whatsoever. The system itself is the universe. Think about it. The system itself is the universe. And to help understand systems and surroundings, let's just draw a nice diagram. Suppose this is my universe, right? It can be my lab, for example. So this is my universe. This is everything in my system's surroundings, right? A small part of this universe is what I'm trying to study. A small part of this universe is what I'm trying to study. This is my system. Right? And the rest of it is surroundings. The rest of it is surroundings. Now, why have I drawn this these weird lines around the boundary? That means it's an insulation, so that anything else does not affect. That means anything else outside this area does not affect my system and surroundings over here. Right? This is a nice little Venn diagram if you think about it. Let me simplify this for you. This is my universe. So I'm just going to say universe over here. And in here, you will find my system, SYS. And outside, you will find my surroundings. Right? This is my system, this is my surroundings. And all of it is the universe. Right? A Venn diagram. And we'll see. Maybe today we'll use this Venn diagram at some place. Let's move forward. We're going to talk about system boundary. Once again, let's start with the Venn diagram. This is my universe, this is my system, and these are my surroundings. Right? So let's see the definition. It is the common surface between system and surroundings. So looking at the diagram, can you point out which is the system boundary? Okay, so is it 1? Is it 2? And the answer is, it's 1. It's 1. What did I say? It's the common surface between system and surroundings. And what do we have? We have the system inside here. We have the surroundings outside here. And the common surface is the surface shared between system and surroundings. Right? So this is my system boundary. Why do we care so much? Well, for one, it's going to help you answer questions in exams. For second, it makes things clear, right? Because types of system boundary affect how our system behaves, how our system changes. And the first thing that, the first type of system boundaries that we'll come across is adiabatic and diathermal. They're both related to heat. Adiabatic system boundaries do not let heat pass through the boundary. So there is no exchange of heat. So system cannot give heat to the surroundings. System cannot take heat from the surroundings. Similarly, we have diathermal walls over here. Diathermal walls can exchange heat. So whenever you see a diathermal wall, then system can accept heat from surroundings. System can give heat to surroundings. Next type of system boundary that we'll come across is rigid. It's movable. And these are related to work. What you have to remember, for now, remember that rigid, there is no work. Work equals 0. And movable, work is not equal to 0. I know that we are not clear on what work is, and we will define that soon. But for now, remember that in rigid walls, work is equals to 0. Movable, work not equals to 0. And if you have trouble remembering this, just remember this diagram. Right? If this guy doesn't move, can he do work? See, all the work will be pending if he doesn't move. You have to be active to do some work. Right? You have to get up. You have to move around. You have to pick up your notebooks. You have to start. You have to put your mind to it. So you have to be movable. There should be motion. If you just lie down, sleep, if you're just looking at the lecture like this, and then checking your phone once in a while, there's no work. Right? Right? You have to move around. You have to be active if you want to work, if you want to learn actively. All right. Moving on. Equation of state. So before that, you can actually take note of all these points that I mentioned over here. Right. Right. So just to emphasize one more time, adiabatic heat is 0. Diathermal heat is not 0. Rigid work is 0. Movable work is not 0. You have to move to do work. Can't just lie down passively and expect to get some work done. Right? Equations of state. We talked about it a little bit in the last class. Equation of state tells us how the state variables are interconnected, how one changes affects changes in others, right? So it's the relation between different state variables. It's the relation between different state variables. State variables, what are they? State variables, what are they? They're measurable properties of the system. Remember last class, measurable properties of the system. Pressure, volume, temperature, number of particles, right? So a typical equation of state, I have written over here. A typical equation of state. So this is a function. Right side, left side, we have pressure. And pressure is written as a function of volume, number of particles, temperature. So it is a relation, right? All functions are relations, right? First lecture of maths, try to remember. All functions are relations. So I've written pressure as a function of volume, number of particles, and temperature. This pressure is related to volume, number of particles, and temperature. If you change the temperature, pressure changes. Change number of particles, pressure changes. If you change volume, pressure changes, right? So pressure is related to volume, number of particles, and temperature. It might seem very vague at this point, and for that reason, we're going to take help of a 3D diagram to visualize it. Right. So we're going to take help of a 3D diagram to visualize it, and the reason I'm saying 3D diagram is because there are 3 variables. Very simple, right? If you have a function of x, you don't need, you just need one x-axis, one y-axis to understand it. If you have a function of x and y, then you need a plane xy points, and then the z-axis to plot the function. So, so this is my function x and y. If you have a function of 3 variables, then you need to define this function across all the 3 coordinates. So I have to tell at each point what the function is. One good example that I can take is temperature field. Temperature field, right? Suppose that what I start doing is I take a thermometer, and at this point I measure the temperature. So at this x, y, z coordinate, this is the temperature. I move a little bit further. At this x, y, and z, I see this is the temperature. So this is how I define a function in 3 dimensions, right? X, y, and z. So at each point, I start by noting the temperature down, and that's my function. So similarly, let's try and draw a 3D diagram. So I'm going to plot one variable, say temperature over here. I'm going to plot another variable, say volume over here, and I'm going to plot one more variable, n. Right, this last one is coming out. It's coming outside. It's coming towards you. So there is temperature, volume, and number of particles which is coming towards you. Right. So on this surface, I have to try and visualize my my pressure. So once again, how do I do it? How do I do it? I go around in this space. Suppose on temperature, number of particles, volume. So I go around in this space. How do I do that? I increase the temperature to go up. I add a few particles to go outside. I increase the volume to go this side. And every time I take a step, I once again take my pressure gauge, this time pressure gauge, and then measure pressure at each point, right? Then measure pressure at each point. So it will have some values everywhere. And we can like so we can define a little bit like this is like some function is present, right? Just imagine that some function is present, because it's honestly impossible to visualize it. Just imagine that some function is present, right? So on this 3-dimensional space, some function is present, and that is my equation of state, right? So I want you to look at this slide and ask yourself questions. Ask yourself questions. Relation between different state variables, pressure equals to FV and T, 3D diagram. What is the common theme that you see throughout this slide? 3D diagram, 3 variables. It's number 3, right? Why number 3? Why didn't I not put any other state variable here? Why did I only choose 3D diagram? Why did I have to take, why couldn't I take 2? So those questions are important, very important. And they are, let's go to the next slide first, right? Minimum variables. So for a pure state, we need 3 state variables. For a pure state, we need 3 state variables to define our state. Any more than 3 state variables are unnecessary, right? I start by measuring 10 things about my system. I don't need 10. I can just take 3 and define my state. For any pure substance, I should say. Any pure substance, if I want to define the state, I need 3 state variables measured accurately. That's all I need. And coming back to the first slide, I said that we use state variables to define the state, and then we use state to calculate other properties. So we just need to measure 3, and once we measure 3, I can define my state, and using the state, I can define other 10, 100, 200, 1000 properties. Once you know the state, it's easy. The problem that scientists, the problem that engineers, the problem that anybody studying thermodynamics has is that we don't know the state. If you know the state, everything is fine. Everything works out. Everything works out really well. And for that reason, ideal gas law is really beautiful. So easy, like the state is just given to you. So for a pure substance, we need 3. Similarly, for impure substance, we need more. If I have a mixture of 2 things, like let's talk about atmosphere. Atmosphere is a mixture of many, many gases. So if I want to define the state of our atmosphere, not only do I have to talk about 3 state variables, pressure, volume, temperature, I also have to talk about in what quantity are these different elements present. For example, nitrogen is present approximately 70%. Oxygen is present approximately 25%. Not sure about the number. So we have to mention those things. We have to mention how much of which gas is present. We also have to mention, is there any reaction happening between them? Is the concentration of something increasing? Concentration of CO2 is increasing every day. We have to define that because that changes the state of the system. So for impure substances, we need more state variables. For pure substances, we need 3. 3 are enough. 3 are enough to define the state. Going back to the last slide for once, ideal gas law is a very nice equation of state. One of the most elegant equation of state that you will come across. So as we discussed in last slide, pressure should be a function of volume, number of particles, temperature. And here is the ideal gas law. PV equals nRT. So I have P equals nRT by V. So you can relate this and this, right? Number of particles, temperature, volume. R is the constant. Number of particles, temperature, volume. So pressure depends on, pressure is a function of volume, number of particles, temperature. Here also, pressure is a function of volume, number of particles, and temperature. So this is the state, this defines the state of an ideal gas. Anything that is supposed to happen to an ideal gas can be visualized using this. PV equals nRT. Right? It's even musical once you say it enough number of times. PV equals nRT. Right? So nice. And you should actually keep this in mind if you haven't already. If you don't have it in your mind, just make a note of it and practice a lot of questions. With practice, it will come fit inside your mind. So PV equals nRT is a equation of state of ideal gases. Similarly, we have to find similar relations to this. for other systems. If we can do that, we can study systems very easily. So we have to find relations like this for other systems, which is the major challenge of thermodynamics. Moving on, we already talked about minimum variables. Now let's talk about internal energy. What is internal energy? It is the sum of all kinetic energy and potential energy of the system. Once again, it is the sum of all kinetic energy and potential energy of the system. Sum of all kinetic energy and potential energy of the system. Keep it in mind, all of it, all kinetic energy, all potential energy. How do I write it? Mathematically is, I say sigma kinetic energy plus sigma potential energy. This is equals to the internal energy. So this is equals to internal energy. Sum of all kinetic, sum of all potential, you add them up, that is your internal energy. And it is represented by the symbol U. It is represented by the symbol U. Right. So U is what we have. Wherever you see U, it stands for internal energy. So U, I'll just write. So this internal energy is equivalent to U. U is what we use to say internal energy. All right. So now we have applications of all that we studied today. And take a moment, read the question carefully, and then try to answer it. Pause the video if you have to think about it, and keep an answer in mind. All right. So let's read. An open system can exchange A matter, B energy, C both A and B, and D neither A nor B. We know this that open systems can exchange both matter and energy. Option C. If I want to draw the diagram of an open system, I say that it can exchange matter, it can exchange mass, and it can exchange energy. Right, so this is my open system. Whenever you think of an open system, you can always think about a cup of coffee. Water vapors come out, some mass is exchanged, heat gets lost if the cup of coffee is hot, heat gets lost over time. So it can also exchange energy with time. So what's the answer? The answer is C. Let's just confirm. Option C is the correct answer. Moving on. So take a moment, read the question and see what it says. All right. Which of the following represents a system boundary? Is it A, surroundings minus system? Is it B, universe minus surroundings? Is it C, system union surroundings? Or is it D, systems intersection with surroundings? All right, think about it. And if you have to pause it one more time, go ahead and do so. All right. So what is going to help us here is that Venn diagram we had in mind. So the Venn diagram we had in mind was of this, and there is our system over here. And let's just erase this extra bit. Right, so we have our system over here, and we have our surroundings over here. And what is the system boundary? Is it this one? The outside one? No, that is not the system boundary. The system boundary is this. It's the common surface between system and surroundings. So this is my system boundary. Right? So how do I find this using this Venn diagram? Let's go by options. Surroundings minus system. If I subtract this circle from this outside region, what do I get? I get surroundings. Again. Why? Because surroundings does not include system. So you might remember, if I take a set 4, 3, 2 and try to subtract 1 out of it, what do I get? I get 4, 3, 2. Because 1 is not present inside 4, 3, 2. I can't subtract it. Right? Similarly, if I subtract system from surroundings, I get surroundings again. Let's look at the next one. I subtract surroundings from universe. So I subtract this outside region from my whole universe. What am I left with? I'm left with my system. So it's still not, we are looking for system boundary. Is it system union surroundings? Is it the sum of the circle in this outside region? No, because that gives me the universe. Right, system plus surroundings is the universe. The universe in thermodynamics has two components, system and surroundings. If you add them up, you get universe back. So even option C is not. So option D must be correct. But let's just check it anyways. System intersection with surroundings. So intersection, if I take a quick example, if I have like 2, 3, 4, and I take its intersection with 1, 2, 3, 5, the answer would be 2 and 3. So when we take an intersection, what we end up with is common elements between two sets. So as a result, the common element, the common surface is the system boundary. Option D is correct. All right. This is a very interesting question. Take a moment, read it. All right. Grignard's reaction is a moisture-sensitive reaction. It is apt to carry out this reaction in a blank system. So Grignard's reaction, you will read it in organic chemistry. Grignard's reaction is, if I have CX type system present, and if I make it, a carbon has 4 bonds in general. If I make it go through R, MgX, so what happens? This R over here replaces the X, and what we end up with is carbon R and MgX2. Or it can be X dash over here, MgX X dash. The problem with doing this reaction in lab is that it is moisture sensitive. Even a little bit of moisture present can completely ruin the reaction. So what should we do? Should we carry out it in an open system? No, that would be very bad. If you carry out an open system, moisture from atmosphere will make your reaction go bad. Can we carry it out in a closed system? Yes. As long as moisture doesn't come in, we can do that. Can we carry it out in an isolated system? Once again, that's fine. Because as long as moisture doesn't come inside, we are fine. So we can take both B and C. And the correct answer is option D. Moving on, thermos is an example of a blank system. This you already know, it's an example of an isolated system, right? We use thermos as an example of isolated system. The old thermoses, the ones which were not very well insulated, are an example of a closed system. But modern thermoses, well insulated, they're a good approximation of an isolated system. So if anybody ever says something is done inside a thermos, you can think of it like an isolated system. Option C is the correct answer. An acid-base neutralization reaction, either it releases heat, absorbs heat, or there is no exchange of it. A very well-known fact in chemistry, you must have even come across this in your earlier classes, that an acid-base neutralization releases heat. It's an exothermic reaction. Right? You might even remember seeing this diagram somewhere, that if you have acid plus base over here, so you have acid plus base, and they convert it into salt plus water. So you release heat in the process. In the process, you release heat. So acid-base neutralization reaction releases heat. It's an endothermic reaction. Option A is the correct answer. Moving on, it's a long question, so take your time to read it. And you have to think about this question, so pause the video. All right. Reaction between HCl and NaOH is carried out in a beaker. A thermometer takes reading of the temperature. Let's draw the picture. That will help us solve this question. I have a beaker and I want to carry out this reaction, HCl and NaOH. We know what the reaction is. HCl plus NaOH gives H2O plus NaCl. Right? Very well known reaction. Acid plus base gives salt plus water. So now what does it say? That there's a thermometer that takes reading of the temperature. And let's put a thermometer here. There's a thermometer that is taking reading of the temperature. And what happens when I mix acid and base? A, temperature increases. Seems correct. Seems correct. If you think about it, acid-base neutralization, exothermic reaction. Exothermic reaction means heat is released and temperature increases. All right, that makes sense. How is option C correct? Acid-base reaction, exothermic, temperature increases. But that's not correct. You have to read the question properly. You have to read the question. You have to visualize the question properly. We see that the reaction is carried out in a beaker. The reaction is carried out in a beaker. What type of a system is a beaker? It's an open system. It's an open, so it can exchange mass, it can exchange heat as well. So although temperature increases initially because it's an exothermic reaction, after a while, this all heat escapes into the atmosphere and the temperature comes down again. The temperature comes down again. After a while, it comes back to room temperature. So the correct answer is C. Temperature first increases, then decreases. If I had carried out the reaction in a thermos instead, then temperature would increase. It will stay the same because the isolated system cannot lose heat. So moving on to next question. Energy of an isolated system can increase, can decrease, can increase or decrease, cannot increase or decrease. And the answer is it cannot increase or decrease. Option D is correct because an isolated system cannot exchange mass, cannot exchange energy. It does not change. It has no surroundings whatsoever. So nothing changes about an isolated system. So energy cannot increase or decrease. This is a very good numerical question. You should solve this and you should also remember the answer to it. Take a moment, pause the question and try to solve it. Try to solve it 3 times to be sure and find the answer. Alright, let's go ahead. Calculate the molar volume of gas at SATP. So we have many terms over here. We have molar volume that we have to calculate. We have to calculate it at SATP. Sometimes in exams you might, like the examiner may not give you what SATP is. I have written it over here. So these are things that you should remember. And what equation will help us here? The equation that will help us here is the equation of state of ideal gases. The equation of state of ideal gases, which is PV equals nRT. And what do we have to calculate? We have to calculate the molar volume. What does the molar volume mean? It means the volume of 1 mole of any gas. 1 mole, only 1 mole of any gas. Right? Molar volume of helium is the volume of 1 mole of helium. Molar volume of nitrogen is the volume of 1 mole of nitrogen. So one thing that the question has already told us is that N is equals to 1. And the question also tells us the temperature, the pressure. So we can just go ahead and start putting it. The value of R, you must know, is 8.314. Value of R is 8.314. So we can just put all the values. I can calculate. I can write V molar now because I put N equals 1 is equals to RT by P. R is 8.314. Temperature is given to be 25. Pressure is given to be 1. So whatever this answer is, that's your molar volume. No, this is wrong because we forgot to take care of units. Very important. Very important. We forgot to take care of units. 8.314. Is this correct units? The values we are using, temperature we are using in degrees Celsius, pressure we are using in bar, R we are using in 8.314, which is joules per Kelvin per mole. So joules Kelvin mole is not related to degrees Celsius, it's not related to bar. The temperature in R is given in Kelvin, but we've used it in degrees Celsius. Units are very important. So let's take 1 second and try to solve this question one more time. Just take your time and solve this keeping units in mind. Alright, so this time I hope you took units in mind while solving the question. So let's take a deep breath and solve this question correctly this time around. I'll erase everything written and this time we'll calculate using the right units. So first, let us look at the units carefully. 1 bar. So pressure is given to us in 1 bar. That's the unit of pressure given to us. Temperature is given to us degrees Celsius. It's never convenient to keep temperature in degrees Celsius. It's always convenient to convert it into Kelvin, and the value of this temperature in Kelvin is plus 273.15. That gives us 298.15 Kelvin. So now we have proper units of temperature as well. We can once again apply PV equals nRT. I'll keep molar volume, N number of moles is 1. So RT by P, and we also have to, we know the value of R now. R is 298.15 and pressure is 1 bar. So just take a look. Temperature given in Kelvin, pressure given in bar, volume to be calculated in liters. So we have to use similar units for R. R has many values. You'll come across 8.314. 8.314 is joules per Kelvin per mole. This is the unit that we find in SI units. SI unit means if volume is in meter cube, if pressure is in pascals, if temperature is in Kelvin, that is when we use this value. But we are not going to use this value this time. This time we are going to use 0.083. This unit is for liters, bar, Kelvin per mole. So whenever you have liter and bar, you use 0.083. So this is the value we're going to use over there. We're going to use 0.083 into 298.15 Kelvin divided by 1 bar. Right? So we can very easily approximate the solution. You can always calculate it. Approximately, we can calculate using converting this into approximately 300 Kelvin. You multiply this by 300, 8.3 into 3, that's around 24.9. So about 24.9 liters. That's our answer. Since we increase the temperature, our answer will be slightly less than 24.9. 24.779 is the accurate answer. Right? So very close. We got close approximation. Sometimes in exams, you just take a look at the options. If the options are not very close, if the options are not written as 24.6, 24.63, 24.67, if they're more like 30, 300, minus 79, then you can take a few approximations. Quickly solve the question to check if you get your answer close to some answer, and then that'll save you time in exams as well. All right. So let's take a look at what we're going to do in the next class. The next class, which is going to be lecture 3, we're going to talk more about heat and work. More about internal energy. So we defined internal energy today. What was it? It was the sum of all kinetic energy, potential energy, and we will understand what we actually mean by that. And then we'll talk about first law of thermodynamics. Finally here, Finally where most teachers start from. So we finally reach first law of thermodynamics, and then there is heat and work, and we'll talk more about heat and work as well, and we'll see how all these three are related to each other. All right. So Rakesh Arya checking out. Have a nice day.